So far, we've discussed how the channel blanket and microcell architectures deal with the challenges of real-world deployment of 802.11n. Along the way, we've exposed some significant shortcomings of the microcell architecture. In this slide and in the following one, we will discuss how the industry is trying to address some of the shortcomings of the microcell architecture. Band-aid number 1 is TPC, which stands for Transmission Power Control. Transmission power control does not work so well. It tries to reduce code channel interference. However, there's a fundamental weakness in the solution. Clients do not alter their power. They still cause the same code channel interference. Band-aid number 2 is dynamic channel assignment. As we mentioned in the DCF discussion, a dynamic channel assignment will disconnect any VoIP call in progress. By the way, DCF can actually choose the wrong channel, increasing code channel interference. Band-aid number 3 is beamforming. Beamforming tries to reduce or eliminate code channel interference. Clients can't beamform, however, so when the client transmits, the same code channel interference problems arise. Band-aid number 4 is 802.11k. 802.11k attempts to enhance the ability of APs to hear each other. It is not very effective as the number of APs and AP density increases because the algorithm does not scale very well. 802.11r attempts to fix the inherent roaming problems of the microcell architecture. 802.11r relies on 802.11k, in particular 802.11k's neighbor reports. And 802.11r, as a result, has not been a very big success. Band-aid number 6 is 802.11e, which can actually cause dropped VoIP calls. Summing up the 802.11 challenges that we've covered, the first is channel bonding, which provides much higher bandwidth but needs twice as many channels. Yet we know that channels are in very short supply in the 2.4 GHz band and not abundant in the 5 GHz band either, especially if DFS operation is not possible. We then took a look at the harsh impact of legacy users on 802.11n throughput. And I talked about the similarly important rate versus range sensitivity of 802.11n and how that can lower throughput too if it's not addressed. Then we took a look at the cell planning challenges presented by 802.11n, in particular cell planning in the 2.4 and 5 GHz bands simultaneously. And we took a look at MIMO, which makes cell planning even more difficult. Finally, we talked about roaming, which is another challenge, and while it is not unique to 802.11n, it's still a problem. Summing up the challenges of 802.11n, the question is, how do the different architectures deal with them? So the first challenge, which is channel bonding at 2.4 gigahertz, in microcell architectures, this is not supported at all. There's just no way to support channel bonding in the 2.4 gigahertz band. On the other hand, the channel blanket provides full support of channel bonding because there's no co-channel interference. Now, channel bonding at 5 gigahertz is better for the microcell architecture, and it's supported, but there's still some co-channel interference potentially, especially if DFS is not available. On the other hand, in the channel blanket architecture, there's full support of channel bonding at 5 gigahertz, as there was at 2.4 gigahertz. And of course, there's no co-channel interference at 5 gigahertz either. Now, as to the impact of DFS, if DFS is not available, as I mentioned a second ago, the co-channel interference in the microcell architecture goes up dramatically. There's no impact to a lack of DFS in the channel blanket because there's no need for the DFS channels. One of the very important byproducts of the channel blanket architecture is that there's no need to use the DFS channels. The use of frequency in both the 2.4 gigahertz and 5 gigahertz bands is so efficient that we have enough bandwidth without having to resort to the DFS channels. Another challenge is rate versus range, and what we realized when looking at the microcell deployment is that there's no way to support very dense AP placement due to the co-channel interference problems. On the other hand, the channel blanket, because it doesn't have co-channel interference, is able to support a much denser AP placement, and for a deployment where throughput is critical, the options available to push the APs closer together so that the average error rate experienced by the clients is much higher. Cell planning. We discussed the challenge of cell planning at 2.4 and 5 gigahertz and the added challenge of MIMO, and it's pretty clear that it's impossible to get to an optimal cell plan in a microcell environment when you have to take into account those two issues. As we said previously, in the channel blanket, the story is 180 degrees different. There's no need for cell planning, and therefore that challenge just goes away. And finally, roaming, which is not unique to 802.11n, but again a very important issue in an 802.11n context, is problematic in a microcell environment, even with 802.11r. The disconnections that can occur as the client moves through a microcell environment is significant, whereas in a channel blanket, the user is going to experience seamless roaming.